Let's see how this formalism works in practice with a simple example. And it's an idealized model of a molecule composed of 3 atoms. The idea is that you have 3 constituents, one in the middle with mass capital M, and 2, one on each side, with identical mass little m, which may be different from the mass of the central atom. There are forces acting between these constituents, and the forces are modeled by elastic springs, which have spring constant K. And it is assumed that there is a symmetry here, that the 3 constituents of the molecule are always aligned on one line. That's why the molecule is called collinear. So they all move only in one dimension along this horizontal line. And let's denote the positions of these 3 constituents by Q1, Q2, and Q3. Let's also say that for both elastic springs that couple the neighboring atoms, the equilibrium distance is equal to some distance b. So the equilibrium distance for both springs, let that be b. What is the kinetic energy in terms of these original coordinates? It's 1/2. Well, it's the sum of the kinetic energies of all 3 atoms. So for the left atom, we have 1/2 mass little m, and then Q1 dot squared. For the central atom, we have 1/2 mass capital M, Q2 dot squared, and for the right atom we have again 1/2 mass little m, Q3 dot squared. We can write it in a compact way as 1/2 vector Q dot ordinary scalar product, and then a coefficient matrix with diagonal entries little m, capital M, little m, acting on the vector Q dot. The off diagonals of this matrix are all 0. This is the matrix T. The potential energy of this molecule, we have 2 elastic springs involved here, and the potential energy of an elastic spring is 1/2 spring constant, and then we have 2 contributions from the 2 springs. For the first spring, well, when the left atom is at position Q1, the central atom is at position Q2, then the distance between the 2 atoms is Q2 minus Q1. This deviates from the equilibrium length of the spring by this distance minus b, minus the equilibrium length of the spring. And this deviation squared times 1/2 the spring constant, that's the potential energy of that spring. Same for the second elastic spring. There we have the distance between the right atom and the central atom is Q3 minus Q2. And then we subtract from that the equilibrium length of the spring, B, and this deviation squared times 1/2 k is the potential energy of the second elastic spring. Now let's say we have an equilibrium configuration at Q1 naught, Q2 naught, and Q3 naught. This is as in the same terminology that we had used before. Let's say this is the equilibrium configuration. And then as before, let's introduce new coordinates that describe the deviation from this equilibrium configuration. Xi, that's defined as Qi minus Qi equilibrium. Now, I would like to leave this to you as an exercise at home, that in terms of the new coordinates, you can write the potential energy in matrix form as 1/2 ordinary scalar product of x, this deviation vector, with following matrix k, so spring constant, minus k, 0, minus k, 2k, minus k, 0, minus k, k, this matrix acting on x. And this is the matrix V. I would encourage you to check at home that this is true. So simply insert the definition of x and perform the matrix multiplication and evaluate the scalar product and verify that this agrees with the expression that we have on the left-hand side for the potential energy. So just a little bit tedious, but it's straightforward to just evaluate the scalar product. Now in the expression for the kinetic energy, since Q and X differ only by the equilibrium configuration, which is time independent, this equilibrium configuration cancels out when you take the time derivative. So you can write that the kinetic energy also in terms of the new coordinates, and that then acquires the form 1/2 x dot scalar product with t x dot. So the Lagrange function in terms of the new coordinates, the deviations from equilibrium, again has this very compact form that we are familiar with. It's 1/2 x dot scalar product with t x dot minus 1/2 x scalar product with vx, where the matrices T and V are the matrices given above. Remember from the general part that in order to express, to write down the general solution, we need the eigenvalues and the eigenvectors of this product of matrices T inverse V. So for general solution, we need eigenvalues and eigenvectors of T inverse V. Now, what about the eigenvalues? The eigenvalues are the lambdas, and associated with the lambdas are omegas. Omega I is simply the square root of lambda I. The omegas are called the eigenfrequencies. Now, the eigenfrequencies of T inverse V are the solutions of the secular equation that the determinant of T inverse V minus omega squared times unit matrix is equal to 0. So the eigenvalues are the omega squareds, but I already write it in terms of omega rather than lambda to get directly the eigenfrequencies. This condition for the determinant is equivalent to the condition that the determinant of v minus omega squared times t is equal to 0. We simply multiply the first condition with the determinant of t, which is non-zero because t is a strictly positive matrix. And then we get this equivalent formulation of our condition. Now, what is the matrix? Whose determinant we have to calculate? Well, let's insert the matrices V and T that we had found on the previous page. And the condition then reads K minus omega squared M minus K 0 minus K 2K minus omega squared capital M minus K 0 minus K minus omega squared M. This is the matrix whose determinant we have to evaluate and whose determinant we have to set equal to 0. You can evaluate the determinant, and again I would like to encourage you to do that for yourself at home to verify that I didn't make a mistake here. When you calculate the determinant of this 3 by 3 matrix, you can write this in the form that's omega squared times K minus omega squared M times omega squared little m capital M minus 2km minus k capital M, and this must be equal to 0. From this you can read off the solutions. Well, there's a factor omega squared, so you see that this condition is satisfied whenever omega is equal to 0. So this is one of the solutions. The first solution is omega 1 is equal to 0. So here we have a case where one of the eigenvalues, and hence one of the eigenfrequencies, is equal to 0. And we'll see in a minute the physical meaning of that, what it implies for the nature of equilibrium of our system. Now the second factor, the bracket here, implies that there is also a solution whenever omega is equal to the square root of k over m. This looks very much like the frequency of an elastic spring with spring constant k. And then the final factor, the second bracket here, that's just use the PQ formula and you find yet another solution, omega 3. It has the form square root of k over m, little m, times a factor which is 1 plus 2m over capital M. So you have 3 solutions of the secular equation corresponding to 3 eigenfrequencies of the system. Once you have the eigenvalues, the eigenfrequencies, you can go about determining the eigenvectors. The eigenvectors must satisfy the equation. Again, I multiply the condition immediately with the matrix T, so we can bring it into the form matrix V minus omega I squared times matrix T applied to eigenvector AI must be equal to 0. This is the condition for the eigenvectors. Let's do it for the first of the three eigenfrequencies, for omega equal to 0. Then the condition reads, well, then this omega squared t drops out. We just have the matrix V. And if you recall the form of that matrix V, it had entries which were plus or minus k. Some were 0, some were plus or minus k. One entry was 2k. We can factor out the k. And then we have a coefficient matrix 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. Applied to the eigenvector A1, which has components 1, 2, 3. This must be equal to 0. Now, if you just look at the, now these are three equations. If you just look at the first equation, this implies, if you perform the matrix multiplication, this implies that the first component must be equal to the second component. Now, if you look at the last equation implies that the second component must equal the third component. So already from these two equations, you learn that all three components of the eigenvector must be equal. So in other words, the eigenvector A1 must be proportional to 1, 1, 1. You can proceed in the same way for the two remaining eigenvectors. So same procedure for the other eigenvalues. And then you find that the second eigenvector must be proportional to 1, 0, minus 1, and the third eigenvector must be proportional to 1 minus 2 little m over capital M and 1. Now note that these eigenvectors are not necessarily orthogonal with respect to the ordinary scalar product. For example, if you take the scalar product of the first eigenvector A1 with the third eigenvector, the ordinary scalar product, then unless you have a very special ratio of the two masses, in general, this ordinary scalar product is different from 0. Yeah? It's proportional to 1 minus 2 little m over capital M, and this is generally different from 0. But if you take our new scalar product, so it's the A1, A3 with the new scalar product, this means that you have to multiply the third eigenvector with this matrix T. The matrix T, remember, is diagonal. The first entry is little m. The second entry is capital M, and the third entry is again little m. So if you apply that to A3, then this becomes proportional to a vector with components little m minus 2 little m and little m. Or if you factor out the little m, you take it in front, it's proportional to a vector with the components 1, minus 2, 1. And then if you take the ordinary scalar product of that with the first eigenvector, you see that this gives 0. So this verifies what we had figured out earlier in the theoretical part, that the eigenvectors are orthogonal with respect to our new scalar product. At this point, we can write down the general solution of our problem. Remember, the general solution has has the structure, it's a sum over I, and then the normal coordinate qi, which is a function of t, times the associated eigenvector ai. Now, we know the first eigenvalue was 0. So the associated solution for the normal coordinate is a uniform motion. And the eigenvector is our vector proportional to 1, 1, 1. And the normal coordinate has the general solution in the form of a uniform motion, so a1 plus b1t. Now let's look at the second component. Here the eigenvector is proportional to 1, 0, minus 1, and the normal coordinate as a function of time has a general solution. There the eigenfrequency is larger than 0, strictly larger than 0, so it's a harmonic oscillation, and the general solution has a structure b2 times the cosine of omega 2t plus a phase alpha 2. And then finally, we have the third eigenvector with components 1 minus 2 little m over capital M, 1, and the associated general solution for the normal coordinate, which is again a harmonic motion with different integration constants, b3 cosine omega 3t plus alpha 3. So we have the general solution for the problem. What does it mean physically? We have a superposition of 3 so-called eigenmodes. Each eigenmode corresponds to one of the eigenvalues and the associated eigenvector. Now, the first eigenmode, that is a uniform motion. And you see from the associated eigenvector that the uniform motion applies to all 3 atoms. So all 3 atoms move in the same way, uniformly. It corresponds to this motion. We have all 3 atoms moving uniformly with the same velocity in the same direction. And here you see why it makes sense that you have an eigenfrequency which is equal to 0. You have an eigenvalue which is equal to 0. Because as long as there's no external potential that captures the molecule, it doesn't matter whether I have my molecule here or if I have my molecule there. I have the same energy. So the position of the entire molecule in space is irrelevant. And each position, whatever position I choose, is an equilibrium position. So in this sense, the equilibrium is not unique, but it's only determined up to translation of the entire molecule in space. Okay, the second eigenmode corresponding to the second vector here. When you look at the eigenvector, the first entry, the first component is 1. So the first entry corresponds to the left molecule, and 1 meaning it moves, say, to the right. The central molecule that corresponds to the second component, the second component is 0, so the central molecule doesn't move, it's at rest. And the third component corresponds to the right molecule, and it has an opposite sign, so it moves in the opposite direction. Yeah, so the central molecule is at rest, and the 2 external molecules, they move in with the same velocity but in opposite direction. So you can visualize that as an oscillation like that. Yeah? So the central molecule of atom is at rest. The peripheral atoms, they oscillate in opposite direction to each other. And then the third eigenmode, when you look at the relative signs of the components of the eigenvector, you see that the two peripheral atoms, they move with the same velocity in the same direction. So let's say they move here to the right. The central atom moves in the opposite direction because the second component has opposite sign. So this corresponds to a physical mode where the peripheral atoms and the central atom move against each other. They oscillate against each other. And each of these three eigenmodes has a different characteristic eigenfrequency, and these are the solutions of the eigenvalue problem.